My name is Majid Ali and today we will talk about geometrical isomerism in this video. What is geometrical isomerism? What is the definition of geometrical isomerism and condition which is required to show geometrical isomerism? First of all, we see where geometrical isomerism is basically arise. Isomer is divided, first of all, isomer is divided into two types, structural isomerism and stereoisomerism. There are 5 types of structural isomerism. And then stereoisomerism is further divided into configurational isomerism and conformational isomerism. What is the difference between configurational and conformational isomerism? In configurational isomer, the isomers are arise due to the breaking and formation of bonds. While in conformational isomer, isomers are formed due to rotation of sigma bond. And configurational isomer is further divided into geometrical isomerism and optical isomerism. Today in this lecture, we will only talk about geometrical isomerism. What is the definition of geometrical isomerism? First of all, we define it. The isomer which arise due to different arrangement of atom in space. First thing which we should keep in mind is different arrangement of atom in space, where with double bonded carbon atom. And second condition is double bonded carbon atom. Suppose we want to see how double bond is formed between a carbon atom. When we say that there are double bonds between a carbon atom, one is sigma bond and other is pi bond. When we look at hybridization of double bonded carbon atom, then it is sp2 hybridization, and we know that in sp2 hybridization, triangular planar is the structure of the molecule. In this, sp2 orbitals are combined to each other to form sigma bond. Sigma bond is formed due to sp2 orbitals overlap. Why? Here, a 2pz orbital or 2p orbitals are combined to each other, then they form a pi bond. When pi bond is formed, then this carbon cannot rotate. Single bond is easily rotated in this direction, but double bond cannot easily rotate. If we hold the board marker in this way, then I want to rotate these two board markers and I force. At one position they cannot be further rotated. So they restrict in rotation. Similarly here, a sigma bond can easily rotate. When a pi bond is formed, this restrict in rotation. When we force it to rotate, then pi bond is break and then sigma bond is rotate in this condition. Let's see which conditions are required to show geometrical isomerism. First condition is restricted rotation. The compound should have restricted rotation. What do you mean by restricted rotation? When we see that when I rotate this, then they easily rotate. When I hold the board marker in this way, then I cannot easily rotate. This is the restricted rotation. Similarly, the carbon atom should show the restricted rotation. How the carbon atom should show? There should be a double bond between two carbon atoms. And the second condition is different group. A different functional group should be present on same carbon atom. Suppose we have an example of 2 butene. into butane, we see that either they are satisfied above two condition or not. First condition, restricted rotation or double bond. Here is a double bond present. First condition is fulfilled, and then we see the second condition is different group on same carbon atom. Here, one carbon atom, there are two different functional groups. Here is another carbon atom, there are two different functional groups are present. And this isomer is known as cis isomer. How we can estimate either this isomer is a cis or a trans isomer? If two same functional group is present at the same time side. Here CH3 is present above. Here CH3 is present above. If two same functional group is present at the same side, then we said it is a cis isomer. And if the same functional group is present on opposite side, here the CH3 group is above and here the CH3 group is below. In this condition, we say that this is a trans isomer. That's why there are two isomers, cis and trans. The second name of geometrical isomerism is cis-trans isomerism. We look at a second example in which two double bonds are present in a single molecule. Here, I have a single molecule, two double bonds are present. It shows geometrical isomerism or not? We look at the condition, restricted rotation, double bond is present. Double bond is present. Second condition, different group on same carbon. Here, carbon, two different functional groups. Here is carbon, two different functional groups. Here is carbon, two different functional groups. It means this molecule can show cis-trans isomerism or geometrical isomerism. There are two isomers are formed within a same molecule. When we look at the first double bond, here same functional group, hydrogen are present below, same side. Then we say that in this region, only in this region there is cis isomer. When we look at the second double bond, the same function group is present on the either side or opposite side. Then we said that this is a trans isomer, and that's why we said that this molecule is cis-trans. This molecule is a cis-trans. In second structure, I only change the position of these two groups. I only change the position of these two. I put this hydrogen on above and CH3 below. And then, what is the name of this isomer? First of all, we see this carbon atom here. Two same hydrogen atom is present below. That's why we say that this is a cis isomer. And when we look at the same hydrogen atom are present on above. That's why we also said that the second double bond is also cis. Then the molecule is cis isomer. The molecule is a cis isomer, and then we look at the another. Here, I only change the condition or position of these two groups. I change this group to below, above, below. Here it is below and here it is above. Then this type of isomer is trans-cis. Why trans-cis? Here, first double bond, same function group are present on opposite side. That's why we said that this is a trans isomer. When we look at this molecule, second double bond, then we said that this is a trans isomer. This is a trans. Then this whole molecule is a trans-cis. And when we rotate up, now I rotate this and this functional group completely. This is below, and then I avoid this on above, and here this is on above or top, here it is bottom or below. Then this molecule is cis trans because in first double bond same function group are present on same side. Here same function group are present on opposite side. That's why we said that this is a trans isomer. Here we said that there is only two double bonds are present in the same molecule. If we say there is a three double bond are present in the same molecule, how many isomers arise? Will you guess? For this, we draw a formula that is 2n. If you have a only single bond in a molecule, then it shows two isomers, cis trans. If you have two double bond within a molecule, then it shows 1, 2, 3, 4. 4 isomer. If we have 3 double bond, then it shows 8 isomer. Here is a formula. Number of isomer. If we count the number of isomers, then we use the formula 2n. 2 raised to power n. Where n is the number of double bonds. How many number of double bonds is present within a molecule? We put that value here, and then we calculate the number of isomers of that compound. Geometrical isomerism or cis-trans isomerism is also shown by cyclic compound. Here is an example of cyclic compound. There is a cyclopropane. Cyclopropane, two conditions are fulfilled. First, restricted rotation. Similarly, if I rotate these two function groups in this way, then the ring breaks. There is a restricted rotation in this ring. And second condition, different group on same carbon. There are same carbon, two different groups are present. Here is the same carbon, two different groups are present. Then same groups are present below. Then we said that this is a cis isomer, and its trans isomer is look like this. Same groups are present on opposite side. That's why we said that this is a trans isomer. Look at another example. Here is a carboxylic group which is attached to a cyclobutane. Same functional group are present on the same side. Then we said that this is a cis isomer, and the same functional group are present on opposite side. One is above and another is below. Then we said that this is a trans isomer. That is all about geometrical isomerism. Best of luck.